So, and also for the invitation to give this present this work. So I don't know the composition of the crowd. Are there students here, undergraduate students or graduate students?
Yeah, I think there are students, but well, I don't really know. Yeah, I think definitely at least undergrad, not below that.
Yes, at least undergrad. Okay, so at least the first section of the talk is aimed towards them, and then we gradually build up. I'll try to define all the terms that I introduce, but you know, we are all here to learn something, so please ask questions, stop me, interrupt me. I'll be very happy to, you know, the more we learn, the better it is. I don't have to reach the end of the slides. Okay, so we'll be talking about predictions, and this is all in joint work with Benjamin Weiss, who's at the Hebrew University of Jerusalem. And before we get a sense of, we formally describe what I mean by prediction, I will, let's look at a very simple example. Let's look at some very simple examples. So suppose I give you, wait, this is somehow, just 1 minute. This one is slightly better. Changing it mid presentation was not the brightest idea. Okay, now it works. So suppose we are given a sequence, I give you a sequence 1, 1, 1, and then I ask you what comes next. So, you know, you will guess that most probably it is going to be 1, and indeed it is. So suppose like, you know, most probably it is going to be 1, but now suppose I give you this sequence, which is going 1, 2, 3, 1, 2, 3, 1, 2, 3. If I ask you again, then you'll probably say that it's going to be 1, right? Because that's what would come next. However, it could very well have been part of a longer periodic sequence where you would have 4, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 1, 2. In which case, the element which follows this has to be 4. Now, as mathematicians, we know that, okay, if I don't tell you anything, if I don't give you any assumptions, if I don't start with any assumptions, then there's no way you can guess what will come next. I could have given you a periodic sequence all through, very arbitrary, right? So the questions that we'll be addressing will be where I will give you some a priori information, some hypothesis, and then we'll try to make a guess. For instance, if instead of giving you a part of the sequence, I gave you the entire past and I told you that the sequence is periodic, then by looking at the entire past of the periodic sequence, you would be able to say what precisely is going to be the next number. And the question which we want to talk about today is that, do we really need to know the entire past to make this prediction, to make this precise prediction? So let's look at let's keep on looking at this simple toy example. So clearly it would be enough to know the sequence along even integers. The reason why this is enough, because if you look at a periodic sequence and you sample it along even integers, then you will still get something which is periodic. So in this particular sequence, if you have 1, 3, 1, 3, 1, 3 along the even integers, you will be able to say that in the present time, it has to be a 3. So this question mark has to be a 3. And clearly, it is not enough to know it along the odd integers, because you don't exactly know which phase of the period you are along the even integers. So in this case, this question mark could either be 2 or 4, and you won't really be able to say precisely what. So if I just know, the only information that I have is that it is periodic, and I'm only given this periodic sequence along odd integers, I cannot predict. If I'm giving along even integers, then I can make the prediction. But the question that we want to sort of, is this really required? Do we really need to look at all the even integers? Can we cut down even further? So we can, and let me give you a precise result of this sort. So set Q is called a periodic set if it is the multiples of a certain integer. So in this case, I've just written multiples of the integer n. And we call a set a periodic star set if it intersects every periodic set. In other words, the periodic star sets, there will be a star here. In other words, periodic star sets contain at least one multiple of every integer. So even integers are periodic star, but odd integers are not periodic star, right? Because odd integers don't contain multiples of 2. Now, suppose I give you a periodic sequence with period p, and we have fixed a periodic star set p. Okay. So there are 2 p's, one which is the small, which is the period, and the other is the subset along which you can see what the sequence is actually. And now what you want to do is you want to predict what x0 is. Now, suppose we know that it is periodic with period p. So if I look at any multiple of p, then the sequence will be the same. But I can't see the entire sequence. I can only see the sequence along this fixed set p, this periodic star set p. But now suppose this, but I don't know what the period is a priori. I only know that it is periodic. So this xi is constant for all. Suppose that xi is constant for all I along multiples of some integer. I don't know what, so here I'm looking at multiples of n for some n. This has to be, because I know that it has some period. I don't know what this number is, but it has to be constant along some multiples of some integer. Suppose that integer is n. But p is periodic star. So it must contain a multiple of np as well. So p is this mystery number, which I don't know. And n is something, it is constant along that sequence. And we know that there must be some integer along which it must be constant. So, okay, so we know that it is constant along that sequence. And we know that it is a multiple of the actual period of, it contains multiples of the actual period. So therefore, I can decide what x0 is given xi where I comes from p. So if you look at this argument and you distill it properly, what you will prove is the following. A set can predict all periodic sequences if and only if it is periodic star. Now, periodic stars are very, very sparse sets, right? Even integers have density half. Periodic star sets can be as sparse as you want. You can choose multiple of 2 to be some number, multiple of 3. You can choose it to be a much, much larger number, a multiple of 5. You can choose it to be a further much larger number. So I have really cut down on the amount of information needed to make this prediction. Of course, when I talk about the amount of information, this is lying a little bit because, you know, how do you take infinite amount of information? There are finitary versions of this, but let's not. But then, of course, you can't predict precisely. We'll always talk about infinite, where we are given infinite amount of information. So now we'll look at another very similar example, which come from rotations. So far, we had looked at exactly sequences which are periodic. Now we look at things which are almost periodic. But does everyone understand this very simple example? And if it is not simple for someone in the audience, they should ask me and then I can explain more. All right, so I'll assume that everyone is with me. Now let's look at something which is almost periodic. So we'll start with the circle and I'll look at the model of the circle given by R mod Z. And I'll take integers x and alpha, I'll take numbers x and alpha in the circle, and we'll rotate x by alpha. So I look at the sequence x, x plus alpha, x plus 2 alpha, x plus 3 alpha. Now, one idea in ergodic theory, a very important idea in ergodic theory, is that you cannot precisely know the location of a point ever. So you can sort of, for example, if you wanted my position right now, you would say I'm in India, in West Bengal, in Kolkata, but you're not going to give anyone the latitude and longitude. Similarly, the fact that this point x belongs to the circle, that's some information, but you won't precisely be giving the person the decimal expansion of x. Instead, you will say that it lies in a certain portion of the circle. So we split the circle into two parts. The first part is this interval 0, half, and the second part is this interval half 1. And if the point falls in the first part, then we record that as a 0. If it falls in the second part, then we record it as a 1. So starting with the point x, we get a sequence in zeros and ones. So let's just go through this. So you start with an x, it lies in the first half, you get a 0. You look at x plus alpha, you again get a 0. Now you look at the subsequent ones lie in the second half, so you record them as ones. So, and the next one is kind of obvious that it will give you a 0. So I've started with a circle, I've started with a number x, and I've started with an irrational rotation, and I have coded it, coded the orbits, coded the places where it is visiting using zeros and ones. Now, suppose I'm given all of this, and now I look at the entire past of the sequence. I look at x sub n, where it notes down whether it visited the second half or the first half. That's precisely this, this set, right? X plus n alpha. I'm asking whether x plus n alpha belongs to half comma 1. So somebody gives me x minus 2, x minus 3, x minus 4, x minus 5, and so on and so forth. And the question I want to ask, can you guess x0 from it? So let me try to gauge everyone's intuition. What do you think? Anyone? So again, let me just go back to this diagram. I've taken this rotation by the irrational number, and I'm coding this visits by which part it falls into. Now I take a number x and I look at the entire past of the sequence. So I ask whether in the past, when was I in part number 0? When was I in part number 1? Is this enough for me to find out what is my present location? Any suggestions? Wild guesses if you don't have arguments, precise arguments. So remember that this alpha is irrational. So each orbit is dense. And this is something that we want to use. So not only we can guess x0, based on this discrete information, we can actually guess what x is. We can precisely say what x is. So let's see why this is true. So if xn is equal to 0, then x plus n alpha belongs to this interval. If xn is equal to 1, then x plus n alpha belongs to half comma 1. So we have that x must belong to this intersection, right? So you look at the points of time when x minus n is equal to 0, and you look at the points of time when x minus n is equal to 1, and you'll intersect all of these intervals, and you'll get interval in the return as a result. And so we can look at this expression, and we can I've written it out here again. So it's the same expression that I had from the last page. And now we are going to write this as a shrinking set of intervals. So this is over all the negative integers. So now I just take integers up until time n, and I look at this intersection. It is enough for us to prove that these intervals shrink to a point, right? That's all we really want to prove. So let's see why this is true. So you have in, which is this complicated object. Okay, so I agree that this is a very complicated object. But after all, what is it? It's some interval of this sort. It is either closed AB or closed in one side, open in another. All these things I won't bother with so much. Okay, so it is some interval of the type AB. Now look at the midpoint of this. Now you know that if you rotate by an irrational number, then you'll get a dense set. If I remember correctly, this was an exercise in the second chapter of routine, but okay, this I'm not completely sure of. Anyhow, I think people in the audience would know this, that if on a circle I have irrational steps, then I'll get a dense subset of the circle. So this will mean that if I look at sort of the opposite end of it, at some point my irrational rotation will be very close to it. So k alpha plus half is very close to a plus b over 2. And once I can do this, you can imagine what will happen. So ik, which is what happens up until time k, is contained in the interval AB. So AB was the intersection of this dot. And it will either give me something like k alpha plus half plus 0 half, or it will give me k alpha plus half plus minus half comma 1. So it will either be an interval of this sort, or it will be an interval of this sort. And this will mean that my interval will split into sort of two parts, and this ik will have radius half of in, and therefore, so this is precisely what I was saying. It will either be of this sort or it will be of this sort. So this means that ik is close to half in. Therefore, the intersection of this, all these sets is going to be a single point. Therefore, X is completely determined by this past data in a measurable way. So given the past of the sequence, we can predict its future. So does everyone understand why rotations can be predicted? That I can tell you the address, your precise location based on which parts you visited in the past. All right. Now, here's an example of something which can't be predicted, which is coin flips. So if you're taking IID sequences, you're independently flipping the same coin, then we know that the sequence that is generated can be predicted. And the past gives you no information of the future. So this is a case where you can't make a prediction. You can predict whether or not you can say whether or not the coin is fair, but that's something of a different, that's a question of a different flavor. You won't be able to say whether you will see heads or tails. You'll be able to say what is the probability of heads and what is the probability of tails. So now that we have these examples in mind, we can make things more formal. So a stationary process is a sequence of random variables. So you have a bunch of random variables, and by stationarity, we mean that if you shift it, it will have the same distribution. So coin flips gives us a stationary distribution. If I look at the irrational rotations, and if I start at 0, then that is not stationary. However, if I choose my starting point according to the Lebesgue measure, then I get a stationary process. And this is I hope people here have heard of stationary processes. Okay. So we shall always assume that our stationary processes are finite valued. So in our example, when we were looking at irrational rotations, our symbols were 0 and 1. And we'll denote this by x sub z. This is the entire process. And we restrict to a subset p, then we'll write it as x sub p. And we will be interested in processes which can be predicted, for which there's any hope of prediction. So these are processes which we'll call deterministic. So a stationary process is called deterministic if there's a measurable function which takes my past, this is a to the power minus n, and gives me the present value. So there will be a function which takes in these past values and gives me the present value. Okay. So this is sort of one of the main definitions I'm introducing in this talk. So I'll let you stare at it for a minute. All right. So as we had discussed before, if I look at the process starting from irrational rotations, that gives you a deterministic process. If I look at coin flips, that is not a deterministic process. A set is called predictive if for all deterministic processes. So here all is very important. All deterministic processes, there exists some measurable function. So this measurable function can depend on the process, such that if you give me the past of the process, along this sequence, I can tell you what my present value is. Okay? So remember, by our definition, since we are looking at only deterministic processes for which there's some hope of predicting, we know that the natural numbers will form a predictive set. This is just by definition. Now, here's a very simple example. If I shift it by k, then I'll still get a predictive set. This is because of the following very simple reason. So I've given the reason here, but let's just go through it together. So this is 0. This is k plus 1. And now I know that natural numbers are predictive. So given the natural numbers, I can predict the present. Given the sequence along the natural numbers, I can predict the present. But this also means that if I look at the process up after k plus 1, then using this, I can predict what happens at k. Using that, I can further predict what happens at k minus 1. And I can keep on doing this till I predict 0. What happens at time 0. So this is why if I shift the sequence by some positive integer, then it gives you another predictive set. Here's a non-example. The odd integers are not predictive. This is because of the example we had before, where we looked at periodic sequences. And we said that, oh, if I told you the periodic sequence along the odd integers, you have no idea what is the periodic sequence along the even integers. So it turns out that the odds are not predictive. In fact, you can do a little more. So here I'll use some terms which I haven't defined, but for people who might be aware of them. In fact, there are weak mixing deterministic processes where x0 is independent of the odd integers, of what happens at the odd integers. So there are things which you can predict what happens at the present given the past, but the odd integers are independent of the present. And these things are mixing in the sense that they do have some asymptotic independence to start with. And the proof uses these products. I won't be able to go into the proofs and Gaussian processes. So if you know enough about Gaussian processes, you might, and its relation to entropy, then you might already sort of sense what the argument uses. All right, so let's go back to things that we understand. As in, I hope that it treats some people in the audience, but you can ask me more questions if you want clarifications. Okay, so I said that the odd integers are not predictive. What about the even integers? Does anyone have a suggestion? It turns out that the answer is yes. But this somehow, I don't have a very simple explanation from this other than it sounds obvious. And for this, I need to introduce some entropy theory. And I can tell you, I can tell you that this is a little non-trivial. It's not completely obvious because of the following reason. This fact that even integers are predictive use critically the idea that these processes are finite valued. If you're infinite valued, for example, you can construct Gaussian processes which are deterministic. Remember that all my definitions of finite valued things. You can construct Gaussian processes which are deterministic, but the even integers cannot predict. So you need to pass through something non-trivial, and that non-trivial thing is entropy theory. Now, there's no way I can introduce to you entropy theory in the next 10 minutes, but I'll try to give you some flavor, and if you have questions, do interrupt me, and I'll try to help. So Shannon is the person who brought about sort of entropy was known before this. It was thanks to Boltzmann. But Shannon really put it in perspective. He brought it, in context of the communication theory, but it soon spread over all forms of new ideas, new technologies, and a very, very revolutionary idea. So what is entropy? So suppose you have a random variable which is taking values in a set A. The entropy of this random variable is defined as the sum of the probabilities log of the probabilities with a negative sign. Now, if this is the first time you have seen this definition, this would probably not make much sense to you. Why, if this is a definition, what is entropy? What does it signify? So I'm going to give you some flavor of what it means rather than investigating this function in more details, because we don't have time for that. Okay, so the first thing that I want you to notice is this is a sum of probabilities log probabilities. Now, each term here with this negative sign is a non-negative term. When is it equal to 0? Well, it is 0 if and only if either this probability is 0, I'm taking the limit then, or this probability is 1. So the entropy Hx is equal to 0 if and only if one of the probabilities, precisely one of them is equal to 1. Right? If one of them is equal to 1, then all the others have to be 0. So that means that my entropy is equal to 0 if and only if the random variable x is completely determined. And this is what I would like you to keep in mind. Entropy 0 means deterministic. Now, let's just look at very quickly, look at the flip situation where the entropy is maximized. So suppose you have the situation again where the entropy is the sum of these probabilities, log probabilities. Now, let's use another simple fact that this is an important fact, that this is a convex function. Now, given that this is a convex function, by Jensen's inequality, we have that the entropy of the random variable, so this was just the definition, and this will be less than equal to, if I would take this down here because I have a negative sign here as well. Well, okay. So what one would, not down here, sorry. The negative sign would give you, I should do this more properly. So you would have log 1 over probability x equal to A. And now you just take this inside and you get this inequality. And that's precisely equal to, since this will cancel out, you'll get logarithm of cardinality of it. And if you investigate when do you have equality, you'll see that you'll have equality only when you have a uniform distribution. So what did we have? We have that the entropy is maximized. It takes this maximum value when you have the uniform distribution. You have the most amount of uncertainty. And we had before that the entropy is 0 if and only if it is completely determined. So entropy is sort of a measure of uncertainty. You can think of it in this way, in these terms here. Similarly, there's conditional version of this, where we say that the entropy of, we look at the entropy of X conditioned on Y, and that is defined by this difference, Hxy minus Hy. And similarly, one can prove that Hx conditioned on Y is equal to 0 if and only if X is a function of Y. You know, I can determine what X is given what Y is. Now, what Shannon did is he was studying random processes, which his applications in mind were coming from the theory of communication, where you have a channel and you have this information which is flowing. And he wanted to capture the rate at which information is flowing from source to receiver. And the way he captured it is this: you would look at the amount of information you had till time n, and then you normalized it by 1 over n, and then you took the limit. And it turns out that this limit exists. That follows for any stationary process. It follows by subadditivity, but we won't go into this. But it turns out that there's this nice addition formula. You can write this as the uncertainty of what you see at 0, plus the uncertainty of what you see at 1 given time 0, the uncertainty of what you see at time 2 given what you see at time 1 and 0, and so on and so forth. And now you can see that there's a tail which is building up. And if you do all of this properly, you use the right theorems, you use martingale convergence, you'll get that that this is equal to the entropy of the present given the past. So entropy of xz is equal to 0 if and only if this object that I have defined is equal to 0. And now if you go back to my previous slide where I spoke about this, that means that this is equal to 0 if and only if my x0 is a measurable function of x minus n. My present is a function of the past. So we have that xz is deterministic if and only if the entropy is 0. And it is easy to see that we won't go through this right now. So ignore this. It's a simple calculation. You can do it on your own. That xz is deterministic if and only if xkz is also deterministic. So you restrict your process to multiples of k, you'll also get a deterministic process. And this is if and only if. And again, this is caution. We need the state space to be finite for this, for all of this. And it turns out this is what you use to prove what I asked. So if xz is deterministic, then multiples of k are also deterministic. So this shows that multiples of k form a predictive set. All right. So far, what have we seen? We have seen that odd numbers don't form a predictive set. Even numbers form a predictive set. And predictions are deeply related to a concept called entropy. Now I can tell you some of my results. I can formulate some of the results which we obtained. So suppose I start with Polish space. So if you don't know what Polish spaces are, just think of the interval 0, 1 with the usual Borel sigma algebra. And there's a probability measure on it. And there's a measurable transformation taking my probability space to itself. So we want this to be a measurable isomorphism which preserves the measure. I'll give you an example in a couple of minutes. So if you are a little uncertain of what is going on, it will become clear soon. So this triple is called a probability preserving transformation. And given a set U of positive measure, we define NUU as the set of times when U returns to itself. So this is the picture you should have in your mind. This is the space X. it's some arbitrary space, measure space, and this is the set U. Now, there's an action on the space. There's a transformation on the space which is acting on it. So when I apply the map T, it will go somewhere. Okay, so this need not be invertible. Let's assume it's invertible. Everything is okay. And I keep on moving this. And I ask for the times when I land up on this set. When do I intersect the set? That's precisely what a return time set is. Okay. So return time sets are sets where you return for some probability preserving transformation. So let's look at a very simple example. So take 2 points. Okay, this is the point -1, this is the point 1. Both have probability half. So now look at this transformation, which takes one point to the other and the other point to the form. So -1 goes to 1, 1 goes to -1. Now, if you take the uniform probability measured on this, then if I apply this transformation, when do I return to myself? I return to myself precisely when the number of times I apply the transformation is even. So this gives us that the even integers are a return time set. Okay. And our theorem is that return time sets are predictive. So this generalizes my simple observation that the even integers are predictive. Here's an example. Look at the circle. And now look at the transformation, which is rotation by alpha. So this gives us an interval -epsilon to epsilon. And now I ask, when do I return by my rotations to this interval? This turns out to be a return time set, and this is predictive. More is true. In fact, one can prove that if you take any predictive set and you intersect with these return times, then it also is predictive. Now, here's the first open question which I will pose to you in this talk. Suppose I instead ask for when I look at n alpha belonging to 0 epsilon. So the question is this set predictive? And we don't know. And this is an extremely important question. It has many consequences, and we have no idea. Here's the second set of results. So there's a lot of definitions. We'll go through this slowly, so don't worry. So suppose I give you, so is everyone fine with this result? Any questions? All right. So the second result is regarding the SIP star sets. So I'll tell you, so this is a sufficient condition. Let's look at necessary conditions. So what are SIP sets? SIP sets naturally come up in additive number theory, sort of additive combinatorics kind of questions. Its full form is symmetric in infinite dimensional parallelepiped, or some people call it symmetric idempotent, depending on where you come from. So it's a very simple object. You look at a sequence S1, S2, S3, S4, and so on and so forth. And you look at all sums and differences that you can form using this set. and then you intersect it with the positive integers. So you have a sequence, you look at all ways of adding and subtracting numbers from the sequence. Whatever you get is my SIP set. A set is SIP star if it intersects every SIP set. Okay, so SIP sets are all sums and differences. SIP star is one which intersects every SIP set. Remember that we had periodic sets, and then we had periodic star sets, sets which intersect every periodic set. So this is a parallel concept. Clearly, the even integers so are SIP star, because if you sum elements like this, then at least one of them has to be even, right? Either S1 or S2 or S1 plus S2 has to be even. Thus, even integers are SIP star. The odd integers, on the other hand, are not SIP star because they do not intersect the SIP sets generated by even numbers. It turns out, so we had this discussion before, that predictive sets, so odds are not predictive, and we generalize this idea. We say that predictive sets have to be SIP star. In fact, we do much more. So this is not an easy thing to prove. Okay, it's not a difficult thing to prove either, but it's an interesting proof. It goes via these products, and that's where SIP star sets arise. And we construct a weak mixing process for which the present is independent outside this SIP set. So, okay, this is now you should complain a little bit. Okay, this is an abstract idea. What does this even mean? What are SIP star sets? So let me give you one property of SIP star, which might strike you a little strange. So it turns out all SIP star sets must have bounded gaps, meaning that if my set is predictive, then the complement cannot contain intervals of unbounded length. Why is that? Okay, so far, just keep this in mind that predictive sets are SIP star. So suppose P was my predictive set. I know that predictive sets are SIP star. Now, what I'm going to do is that since there are unbounded intervals in the complement, I can construct an SIP set inside it. So in the first interval, I can choose an integer S1. Then I'll look for a very large interval outside that, which is in the complement of P. And there I'll subtract off S2 and add S2. Then I'll take these 4 integers and I'll look for an even bigger interval where I can fit an S3, all the differences and all the sums. And I'll keep on doing this. So if I have unbounded intervals, I can fit an SIP set inside it. So the fact that I proved SIP star proves that predictive sets must have bounded gaps. So the sufficient conditions for a set to be predictive are that the return time sets are predictive. Necessary conditions are that predictive sets are SIP star. The following question arises naturally: are sufficient conditions necessary? Necessary conditions sufficient? Now, one of the theorems I stated is that predictive sets are SIP star, which also means that predictive sets are bounded gaps. We don't know whether this is open. We don't know if SIP star sets are predictive. So this is very deeply related to the question which I raised earlier, which asked whether this set is predictive. So this is a question which I had asked earlier, and these two questions are very much related to each other. It turns out that return time sets, this theorem, where we say that return time sets are predictive, this gave us sufficient conditions. We know that there are predictive sets which need not be return time sets. And this is due to a theorem that I have with Benjamin Weiss, which says that if I take the natural numbers and remove the squares, then that is a totally predictive set. So not just it can predict the present, it can predict the entire sequence. So for all I. So my definition of predictivity was that x0 conditioned on this should be equal to 0, right? I can write x0 as a function of the rest. In fact, I can write xi as the function of the complement of the squares for all I in Z. So thus this set is totally predictive. Now here's a question which you should automatically ask. So it can predict everything. Why are you being so specific? Shouldn't it be that I can predict some information, I can predict using some information. If I remove a very, very sparse sequence, then I should still be able to predict. I should still be able to say what happens in the present outside the sparse set. And the notion of sparsity, which interests me personally, comes from this condition. So my subsequence nk, so sequence nk is an increasing sequence such that the differences are also increasing. We prove that the complement of, we want to prove, this is a question, this is a big open question, whether the complement of a sparse sequence is totally predictive. So I prove this in the case of squares. In the case of cubes, it is open. And it's not open for some trivial reason. This question is related to deep questions in harmonic analysis, which we will now discuss. And the only partial results that we could obtain use Fermat's last theorem. Jyotsuru, how much time do we have? So it's already about 15 minutes, I think, from when I started. So do I have 5 minutes, 10 minutes?
Yeah, sure. You can take 5 more minutes also. So we have 5 minutes,
more.
and you can take 5 more.
All right.
Yeah.
I didn't hear you properly. Sorry?
Yeah, so I'm saying you can take more time. Yeah, you can hear me?
Yes.
Yeah, so you can take more time, 5 more minutes.
I heard you now. Okay, all right. So it will be enough for me to state what is the relationship. So from here on, we will look at, so we'll switch gears and we'll forget about predictions for a little bit. And I'm not going to make the relationship very clear right now because it's complicated. So we are going to look at measures on the circle, which are complex valued, outer, inner, regular, finite, and on the group R mod Z. So all nice things, except that now we'll be looking at complex valued measures. The Fourier transform will be defined by mu hat. Lebesgue measure is mu sub L, and the support is defined as the places where the Fourier transform is, or the function is non-zero. A set is called a reset if for all measures mu for which the support of the Fourier transform is contained in the set, we must have that the measure is absolutely continuous. So if there's a measure whose support of the Fourier transform is contained in the set P, then it is absolutely continuous with respect to Lebesgue. Okay. And one can prove several properties of them. For example, it turns out by this theorem that the natural numbers form a reset. And what Rudin proved is that if you take a very rapidly increasing sequence and you append it to the negative integers, then that again forms a reset. So any measure whose Fourier transform is supported on this very sparse set is a reset. And Meyer took these results and he showed that the union of the negative integers and the set of squares is a reset. We were very surprised to find out that his proof was exactly the same proof as what we use for totally predictive sets. Amazingly, the question for cubes is also open in this context. So we don't know that the union of the negative integers and the set of cubes is a reset. So this is a question which I would like to ask, and where if you add a sparse set, do you still get a reset? And there's a nice proof by Wallin, elementary proof by Wallin, which tells you that you don't know whether mu is absolutely continuous. So you have a measure mu whose Fourier transform is supported on the set P. You don't know whether mu is absolutely continuous, but its convolution with itself is absolutely continuous. So we are very close to the result, but not quite there. So what we could prove, so there's some relationship with predictive sets, which we won't go into. What we managed to prove is the following, that this is what we wanted, that if I append the cubes, then I get something absolutely continuous. What we managed to prove that if mu is a probability measure, not a random measure like this, and if the support of mu hat is contained in the negative integers and q, then mu is absolutely continuous. So we are sort of almost there. Well, okay, not really. I think there's a huge distance going from here to here. So, and the proof uses like it's completely trivial if you ignore this line. And I won't go into the details of the proof because I shouldn't take more time. So here are some questions. If you're interested in probability, you can think about this question. If you're interested in harmonic analysis, you can think of this question. And I would be interested in the answer either way because there seems to be a very deep relationship between them. And we have some actual proofs. We know something about the relationship between them, but this is still something that we are thinking about. And that's all I have to present. Sorry for going 1 minute extra, but that's all I have to say.
Thanks, Nishant, for a really nice talk. Are there any questions?
Just one question, Nishant. So
yes,
you said predictive means x naught is a function of the past values at minus p, right? Xn?
yes.
Okay. What is totally predictive? I missed that.
Oh, so let's check this out. So is predictive if let's not write it in terms of entropy. If for all deterministic processes, x sub z, we have that x0 is a function of x at minus 1, measurable function.
Right.
And totally predictive. Would be the same thing, except that you would say that xi is a function of x minus p for all I in Z. So you can find the entire future and not just the present.
I see. So from the predictive, it follows that x1, x2 all are functions of x minus p, right?
No, it doesn't. It only follows that x0 is so.
But you have stationarity, right?
Yes, we do. But
for instance, stationarity does not help in getting x1.
Stationarity does not help. In fact, so here's another question.
Oh.
So let me first give an example.
Oh.
So look at p equal to the even integers.
Right.
Then you know that x0 is a function of x on the negative integers, but we don't know anything about x1, because now if you use stationarity, then you only know information along the odd integers. Right? You would be interested in this quantity.
Right.
And this is like knowing the odd integers, so we can't say anything. But you actually are heading towards a very, very interesting question, which we also don't know the answer to. So here's the question. Suppose P is predictive. Can you say anything about the shifts of P which are still predictive? Is the set of integers such that I plus P is predictive non-empty? Yeah, I can even say non-empty. So I make this natural number so that this does not become a trivial question. So even this, so we should be able to use stationarity, and this should be true. We couldn't do it.
Yeah. Okay. And at some stage you said weak mixing. Why did you need weak mixing?
So the way we used weak mixing is in the following sense. So we said that the odd integers can't predict the present for all deterministic processes.
Right.
But the kind of examples which I gave to you are periodic ones. Right? You look at a periodic sequence and you know that the odd integers. Now you don't. You would imagine that if you have some sort of asymptotic independence, then such examples should not arise. But it turns out that even then you can construct examples. So that's where weak mixing played a role. So we constructed weak mixing zero entropy processes where the present is independent of the odd times.
I see.
So since you probably know more about this than I do, it's essentially we construct a Gaussian process with this property, and that corresponds to constructing a continuous measure whose a continuous measure on the circle whose Fourier coefficients are supported on the evens. And one can do this very easily using Riesz products. So you look at Riesz products and you look at the corresponding measure on the circle, And that's precisely where we also use this SIP property. So there was these sums and differences that we were forming. Now, if you look at these products, then it's you're looking at sums of symmetric exponentials, and you'll get sums and differences exactly of that form, and that's where SIP sets also arise. And yeah, zero entropy corresponds to singular spectral measure. That's that's the where all of this comes.
Okay, thanks.
So yeah, I don't know. I have maybe it's true. Perhaps you already said that, but being new to all this, so whatever you said is about discrete processes, right?
Yes.
So are there results for this continuous processes?
Right. So this is an extremely interesting question, and let me see where I can start. So the problem is I'm forgetting a very important name. I remember the theorem, but I don't remember the name or the person who proved the theorem. So maybe someone in the audience would know, maybe you would know. Do you remember that if you look at, so you want the condition for x0. So suppose you're looking at the circle and you want the, so let's get a new page. How do I get a new page? Here it is. So you want to okay, so there are few things which I should say first of all. So what changes between discrete processes and continuous valued processes? The problem is that the idea of entropy changes drastically. So when you're looking at finite valued processes, then there's a very easy way to partition, and this address story works very well. But when you have an infinite valued process, then somehow this idea of prediction and the idea of entropy start diverging from each other. And so the definition, let's keep the definition same. Okay. So x sub z, now these are infinite value. And we will call this, this will be L2 valued. So this is L2 process. And we want to know when is this predictive. So this would correspond to, is there a measurable function phi such that is equal to x. So if there is such a function, if there is a measurable function of this sort, we can call x sub z as deterministic. So it turns out this is related to the following question, which you might be familiar with. Take a measure mu. Now mu is going to be a probability measure on R mod z. And we will look at the question, and we will look at the polynomials, 1, z, z square, so on and so forth. And the question which we want to ask is the following: does 1 belong to the closed linear span of z, z square? This is the question which we want to ask. Is the question clear? Now, how does this correspond to our question of determinism? Well, it turns out that if you generate this mu in the proper way, if mu is what is called the spectral measure of the process, so what is the correspondence here? I hope I'm not giving a longer answer than you want to hear. This mu hat will be the expectation of x0, xn. This is all zero mean. So let's assume that. So it turns out that, so you can write mu as f d mu l plus the singular part, some mu prime, right? And what one can prove is that one belongs to z square, this closed linear span, if and only if the log of the density with respect to mu l is not integrable. Okay, so I'm a little ashamed that I don't remember the name, but I remember the mathematics somewhat. So, and this, if you look at it, this relates to the question whether, so this is completely equivalent to whether x0 is in the closed linear span of x1, x2, and so on and so forth. So can you predict x0 in a linear fashion corresponds to this fact. But now you can do many very weird things. For instance, you can consider a measure which is of the following sort. So this is your circle, and take the Lebesgue measure on half the circle. Now, if you do this properly, then the Fourier coefficients for this measure mu hat of 2n is equal to 0 for all n, right? And so the Fourier coefficients vanish on the even integers, but clearly, if you look at the log of the density, it's going to be infinity on the rest of the half, right? Because your measure is supported on the other half. So it turns out that you will have prediction. You can predict using the future, the past, but you can't predict using the even integers. So it's a completely different ball game. There's a completely different set of questions. So here is a question which we don't know how to answer. And this will tell you how little we know about this. So we are going to call P, I'm inventing names right now, you won't find this in our paper, as super predictive if for all deterministic